This is Logic and Computer Design Fundamental class. And in chapter 9, we will focus on memory basics. So here are some definitions and terminologies related to memory. The memory is a collection of storage cells together with the necessary circuits to transfer information to and from them. The memory organization is the basic architectural structure of a memory in terms of how data is accessed, and we will see more details about this in the next slide. The random access memory, simply RAM, is a memory organized such that the data can be transferred to or from any cell. And the memory address is a vector of bits or a group of bits that identifies a particular memory element. A memory bit is a single binary memory digit, meaning it's either 0 or 1. The memory byte is a collection of 8 memory bits accessed together. The memory word is a collection of binary memory bits with a specific size. Usually it's 1 byte, meaning 8 bits, or 2 bytes, 4 bytes, 8 bytes, etc. The memory data, a bit or a collection of bits to be stored into or loaded from memory cells. The memory operations, typically they are read and write operations over some data elements, whether they're bits, bytes, word, etc. Now, to understand a memory organization better and the other terminologies, in this set of slides, we are focusing on memory basics. So the memory organization is actually organized as an indexed array of words. The value of the index for each word is the memory address, often organized to fit the needs of a particular computer architecture. Some historic significant computer architecture and their associated memory organization will take them as examples. The first one being the Digital Equipment Corporation. They have the address, 12-bit address, to address 2 to the power of 12, which is 4,096 different locations. The data is 12-bit words. Even though they are the same, there is no direct relation between them. The IBM 360, the address is 24 bits address, which will address 2 to the power 24, 60 mega different or 60 million different location. The data is 8-bit bytes. You can see the differences between the two. And the third one is Intel 8080. It's an 8-bit predecessor to the 8086 and the current Intel processors. The address is 16 bits or 16-bit address to address 2 to the power of 16, which is 64 kilo different location. The data is 8-bit bytes. You can see now they are different, the address and the data in the Intel 8080, also in the IBM 360 is 24 and 8. So these are different memory organization where are the address bits and the data bits are specified. To understand the memory block diagram, if you have this block where it represents a memory unit, you will have K address line, which are the basic inputs. There are K lines of them. This is representing the address. It addresses 2 to the power of K different words of the memory. So you have 2 to the power of k words, as you can see here, starting from word 0 up to word 2 to the power of k minus 1. Each word of them is n bit. So you have n bits per word. As you can see, word 0 having from bit 0 to bit n minus 1. And you have some control lines. You have read and write control. They are, if read is equal to 1, it means that the read operation is allowed. If write is equal to 1, it means that the write operation is allowed. Now, since we have for each word n bits, then the data input lines is also n bits, and the data output lines is also n bits. Basically, you call the memory by 2 to the k word, n bits per word, or you call it this way, 2 to the power of k times n bits. To see an example, let's consider k is equal to 3 and n equals to 8. The easy one is the n. Since you have 8 bits, it means that the input, the data input is 8, and the data output is 8, and you have for each word 8 bits, starting from 0 to 7. Now, since the address line, you have 3 address line, this means that there are 2 to the power of 3, which is 8, different words, starting from 0 to 7. If we change 3 address line to 4, this means you will have 4 address line here, and you will have 2 to the power of 4 words, which means you will start from word 0 up to word 15. So notice, now by changing the k, we changes the number of words or the number of different distinguished words, but we kept the same number of bits per word, so we still have 8. Now, this example, we look at it from different angle. The memory is called 8 words by 8 bits. You could call it this way, or you could call the memory this way: 2 to the power of 3 words, 8 bits per word. Usually in textbooks, they call them this way. Now, this is a memory with 3 address bits and 8 data bits that has k equal to 3, n equal to 8. So we have 2 to the power of 3, which equals to 8 different addresses labeled from 0 to 7 in this table, as you can see, from 0 to 7, in binary from 000 to 111. This is the memory address. Now, since we have 8 bits, which is representing with n, it means that in each location that is addressed by this address line, for example, the location number 0 is having this data, which is 8 bits, as you can see. Similarly, for the different addresses, they have different data. This data is the data represented here is random. Yeah. For example, in this part here, we are having the maximum number, if it is unsigned value, 11111111, which is 255. Now, the basic memory operation on the data, we have read and write. We read or load from the memory, or we write or store to the memory. The addresses specifies the memory location to operate on. By saying operate or access, we mean either read or write. The address lines carry this information into the memory. Typically, k bits in the address line specify 2 to the power of k different locations. An operation being a reading the memory or writing the memory, and the operation read memory reads or loads a data value stored in the memory. The operation happens like this. First, we place a valid address on the address line, and then we toggle the memory read control line. We wait a little bit for the data to be prepared from the memory and become stable on the output lines. This way, we complete the read. For the write memory operation, it writes or stores a data value to the memory. Again, we place a valid address on the address line. We also need to place a valid data on the data lines since we are trying to write. So we supply both the address and the data. And then we toggle the memory write control lines, and the write operation will be completed. The main difference between the two is actually obvious, but from the memory operation point of view, in the read, you give the address and you wait for the data to come out from the memory. In the write, you give both the address and the data to the memory for the write operation. Now, this is the timing diagram. We will discuss the timing diagram for the read and also for the write. So we will start with the read. You can see that we have a clock. In this timing diagram, we have T1, T2, T3, T4. That's enough to do the read operation and also the write operation. And after this, we repeat again, starting from T1. You'll notice that we have an address, a memory enable, the read and write control signal, and the data output. So we start by supplying the address in the address lines. As you can see here, the address will be valid the whole time. So we will give the address here. There will be a certain address that is valid the whole time from T1 to T4. During this time, the memory enable is the one that tells us that this address is valid. So we have a memory enable signal to enable any operation on the memory. Now we have this control signal where it's having the read and the write in a single line. If you want to make or to perform a read operation, the signal here will be equal to 1. If you want to do a write operation, it will be the opposite since you have write bar. It will be 0 in the right case. Now what happens in general in the read operation, you give the address, wait for some time, and then after this, the data will be valid in the output lines. Now you can see if the clock cycle is 20 nanoseconds, for example, in this timing diagram, we waited 3 cycles, which is 60 nanoseconds, and a little bit more to make sure the data already presented in the output lines. So we waited, for example, 65 nanoseconds, 60 plus 5 more nanoseconds. It's very important to know the timings related to the read operation and also for the write operation. Let's go to the write and notice what happens in the control signal. In the read, it has 1. In the write, it have a 0. During this time, the right operation happens. Again, we have 20 nanoseconds and 4 clock cycles. The address is valid throughout the 4 cycles. The memory enabled also is valid. The memory is enabled. And what we did in the write operation, we give or supply the address, and we also supply the data starting from the clock number 2. So we give some time for the address to make sure that we targeted the correct location. And after that, we start doing the writing operation. We supply the data, and the writing will happen during this time. You could see that you need to finish the write before this time happens, before the data become invalid. So what happens? We needed for this specific timing diagram, we needed 1, 2, 3, 4 cycles to finish the write. 4 cycle is 80 nanoseconds, but we needed to finish the write before that. So we give like a guard 5 nanoseconds, and we needed the timing requirements here is we needed to finish the write or the write cycle in 75 nanoseconds. There are some critical time with respect to the edges of the write pulse 101 being like this. We assume a rising edge or a positive edge clock. So the operations will happen in every rising. That's for the read and also for the write. And let's discuss sometimes for the write cycle, for example. The address must be established at least a specific time before the 10. If this is a clock, which is 101, this is the same thing. So before the 10, before this time, the address must be established. Now, it's also must be held for at least a specific time after the 0 and 1, after this time, after this 0 and 1. It needs to be held for some time. Usually we call the time here setup time. We call the time here hold time. Why we need this specific timing for the address? To avoid disturbing stored content of other addresses, to make sure that we are selecting the address that we want to deal with. Now, similarly for the data, it must be established and held for specific time before 0 and 1. Before this time, you need to make sure the data already established and also it's held for some time. Why this is for data? To make sure that we are writing the data correctly. Now, as there are so many aspects related to the memory. So to understand different aspects, we need to know the types of RAMs or the types of random access memory. Here we are working with only RAMs, and in terms of access, we have in terms of the type of accessing the memory, meaning the technology behind it, it's either static, where the information is stored in latches, or dynamic, where the information is stored as electric charges. Now, one disadvantage about the dynamic, the charge with time, it leaks out, especially if you are storing a logic 1. With time, the voltage value leaks out and it tends to go back to 0 with time. And to avoid this, we need to do periodic refresh where we supply it again to full voltage to make sure that it's kept at 1 and never touch 0. If you look at it from the dependence on power supply point of view, we have volatile and non-volatile. The volatile RAMs loses stored the information when the power is turned off, and most, if not all, the RAM are volatile. The non-volatile memories retain information even when the power is on. Now, to see the differences between the static and dynamic in a more detailed way, we see it here in this slide. This is the static RAM, or simply SRAM. This is the dynamic RAM, or simply DRAM. The basic element here is the D latch, which is what we see here. And we know the D latch, you have a data, and you have D going, the data input goes to the D, and the output will be in the Q. You have a tri-state buffer here to control if you are selecting this latch or not. You have also control here for the write signal if you want to enable the latch to be written to or not. So this D latch is actually the internal design of it is two inverters back to back, which is like this. This is one inverter, this is another inverter, and they are back to back this way. So if the value here is 0, it will be toggled to 1. It will be toggled back to 0 and 1. So this way you are saving this value and this value. In the dynamic RAM, the charge stored in the form of electric charge in a capacitor. So we have a capacitor here. If it is fully charged, then it's storing the logic 1. If it is not fully charged or empty, then it's storing a 0 value. We have this NMOS transistor to control the data in. And we could have also, similar to the SRAM, we could have a tri-state buffer to control the output as well. As you can see here, we would have many components in the SRAM, but here we have only a capacitor controlled by a single transistor as the DRAM. So the data here, going back to the differences, the data remains stored in the cell until it is intentionally modified. So there is basically what we are trying to say here, there is no leakage, but here the charges leak out with time. Thus, we need to refresh the data every few milliseconds. The static RAM is very fast. The access time is only 1 nanosecond, typically. The dynamic RAM is slow, and the access time could be up to 60 nanoseconds. If with new generation, we reduce the access time of the DRAM, know that it's also reduced for the SRAM. It needs more space since there are many components. It needs less space here. And for the same reason, the SRAM is more expensive than the DRAM. It's used actually as cache, whether it's level 1 cache, level 2 cache, or level 3 cache. But in the dynamic RAM case, it's used as the main memory. It's good to mention, if you have a CPU, the closest storage element to the CPU are the registers. After that, we have a bigger storage, which is level 1 cache, and then level 2 cache, and then level 3 cache. And after that, we have a really big storage, which is the main memory. So the caches here, we talked about the register in a previous video detail. Those 3 caches are designed usually using SRAM, and the main memory is designed using a DRAM. From the power consumption point of view, the SRAM consumes powers only when it is accessed. But the DRAM consumes power even if it's not switching. It could be even when only the power, whenever the power is on, it's already consuming power. However, in the SRAM, even if the power is on, the power consumption happens only when there is an access. This is another subject related to power consumption. And on this time, know that there are two types of power. There is dynamic power and there is static power. The dynamic power and the static power, let me write it this way, the static power and dynamic power. This power consumption happens in the SRAM and it happens also in the DRAM. But the static power component is much more in the DRAM because of the leakage. Now let's see different organization of memories as examples. We will organize the cells or the memory cells in certain ways to understand how the memory organization is happening in new memories. We will start with simple memory organization and then we will build up. So we have 2 to the power of k word times 1 bit RAM integrated circuit. And to build this integrated circuit, we need a decoder. And we also need three-state or tri-state buffer. The decoder we needed to decode the k address lines to 2 to the power of k words. So for example, if you have this RAM that you want to design, you want to design 16 by 1. So the output is only a single bit. You read a single bit or you write a single bit, and you have 16 different locations. So here is the cells starting from 0 to 15, and you have a single bit per word. So what we need is a decoder. It takes the 4 inputs here, and it generates the outputs where one of the lines is active and the other lines are deactivated based on what is the address. So for example, if you have the address 0, 0, 0, 0, this one will be 1 and the rest will be zeros, meaning that you are accessing RAM cell 0. Now, you also have the normal inputs and controls that we discussed. We have the read and write control. We have the data inputs in case you want to write a data, and you have the data output in case you want to read the data. Notice that this is the usage of the tri-state buffer on the data output, which permits the RAM integrated circuit to be combined into RAMs with bigger sizes, as you can see here. You can also see the chip select or the memory select or the memory enable. This also helps us if we want to build bigger memories from smaller ones. And we will see those benefits in the coming slides, starting with this one. Now, the cell organization, instead of having a very long rectangle like this, it's better to design memories in a square shape. So the decoder size and fan-outs can be reduced by using a two-dimensional array. Now, the 4 address line that we had in the previous slide, those 4 lines, we will separate them into 2 and 2. So we have a smaller decoder here, 2 to 4, and another decoder 2 to 4. This is called the row decoder. Now we have 2 dimensions, so we have rows and columns. So this one is called the row decoder. This one is called a column decoder. So these decoders, we have a row decoder that generates the row select and the column decoder that generates the column select. So for example, if we want to select the RAM cell number 9, let's say. So we should know where exactly is the least significant bit and the most significant bit. So let me list them here: A0, A1, A2, and A3. We know that 9 in binary is 1, 0, 0, 1. So we will put 1, 0 over here. And we will put 0, 1 over here. 1, 0 will select the number 1 column. So this will be 1 and the rest is 0. This is the output of the decoder. For this one, we will select this one here. So this will be 1 and those will be 0 because we have the value of 2. So we are selecting 2. As you can see, this one is activated. This is 1 and this one is also activated, which means that we will choose cell number 9. Now you can see the organization is happening this way. And now we have the data input going to every column here as an input, and here, and here, and here. The read and write control signal also goes to the read and write for each one of them. Now for the output, since we will select one of the outputs, only one. So we want this one to be in the output. You can see that the data output is going this way. And only one of them will be allowed to go to the data output. Notice that here we have 4 inputs or sec. Now the chip select is selected here. This means that we will select this memory, and it's also going to be the control of the tri-state buffer. All the modern memories have this architecture where the decoder is split into 2, row decoder and column decoder. Now the sizes of the decoders, the best case is if we have the same size, 2 to 4 and 2 to 4. But sometimes, especially if you have an odd number of address lines, one of them will be bigger than the other. Now, how to make larger memories and how to make wider memories. First, we will talk about the large memories. What we did here, if we have a 4-word by 1-bit memory, and we would want to construct a bigger memory where it has 4 different words, 16 different words, we can do that by repeating this one 4 times. So we have this memory and we repeat it 4 times. Now we need to figure out how to connect them together. Since we have only one output data that is valid from those 4 different memories, we will connect them together to generate a single output. That output would be 1 bit in this case. Now, to select the correct location, we need to manipulate the address lines this way. First, since we are building 16 bits or 16 different words, we need 4 address lines. Those 4 address lines, the least significant 2 bits will be connected to memories directly. We connect them here, 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 and here. The most significant 2 other address lines we connect them to 2 to 4 decoder. This will generate 4 lines for us, and we will pick the correct memory this way by using the chip selects. So if we have the memory location that we want to access in the lower 4 words, we need to make this 0, 0 to make sure that this is 1 and the others are 0, which means that we need to chip select this memory and we don't select the others. If, for example, we want the higher 4 bits or 4 words, one of them, this one would be 1, 1 instead of 0, 0. We will have 1 and 1, which means that this would be 0. This one here is 1. So we select this memory location instead of the last one here. You can see how we manipulate the chip select to build larger memories. For the input data and the read and write, we also connect them to all memories. So basically, to build larger memory, we only manipulate the address lines. The other lines, even some part of the address lines, is connected to all memories. But the higher or the most significant bits are the ones that are used with the chip select. So, in short, we connect the address and the read-write lines in parallel. We connect the input and the output data lines also in parallel, and we use a decoder to control the chip select with the most significant address lines. Now, if we want to build a wider memory, meaning now the data bit, which is what we call N, is now wider, it's more. So instead of having 1 bit that we input or output, now we have 4 bits. We kept the same number of words. Now notice that we also used 4 copies of a 4-word by 1 bit memory. And now we will manipulate these files. So to do this, we connect the address and the data, also the read and write control lines in parallel. So you can see the read and write and the address is connected in parallel, as you can see here. Now for the inputs, since we want a wider input and a wider output, previously we had a single bit data input and a single data output. A single bit data output. Now we have 4 bits input and 4 bits in the output. And to do this, we connect the least significant bit of the inputs to the first memory location, the second to the second, the third to the third, and so on. Similarly, for the output, we get the output of the first one, and then the next one, the next one, and the last one, this one. For the chip select, now we select all the memories at the same time. So basically, what we did here, to get a wider memory, we increase the number of the data in the input, and we increase the number of the data in the output by using them in parallel. Similarly for the inputs. For the chip select, we connect it to every one, or all of them will be connected to the same chip select. So in summary, we connected address, data, and the read and write lines in parallel. We keep the data lines separate. We connect the chip select line also in parallel to make the memory wider from 1 bit to 4 bit, as you can see in this example. Now, Here are some of the concepts aggregated together in one slide. If we know that this one here is the memory inside your laptop or your PC. It's called 2 GB DDR3 dual inline memory module, which is shortened to DIMM. You can see those pins here, the yellow ones, are responsible for transferring address, data, and control. Now here we have 8 black chips. Those black chips, each one of them is 128 megabytes. So we have 8 of them in the front rank, which is what we see in front of us in the slide. We call this rank 1 or side 1 or the front rank. And there are 8 more in the back that we can't see. It's not in the slide. And we also can call it rank 0 or side 0 or simply the back rank. So we have 8 in the front, 8 in the back. The total is 16 times 128 megabyte for each chip, which will total 2 gigabyte, which is what we have in this DIMM. Now, by saying DDR3 is the technology that is used here to store bits. Since it's a DRAM, then it has this architecture, every cell will have this design where you store the data in a capacitor and you do refresh every once in a while. Now, to see how we came up with each cell and how is it placed inside this DIMM, we take one of them, for example, and we zoomed inside it, as you can see here. In detail, we have different banks. We have here 8 banks. Each one of the bank will generate a single bit. So if you want to access a certain location, you will get 1 bit from here, 1 bit from here, 1 bit from here, and then you will end up with 8 bits. Now, each bank is organized in, for example, we took bank 1. It's organized, as we said, as rows and columns. So you have rows and columns, and we've seen this in a previous slides. And you can use decoders to access the required cell. This way, you get one of the cells, which is actually a DRAM cell. So you can get 1 bit from here, 1 bit from here, 1 bit from here, and so on. And you accumulate 8 bits, which will give you a single byte. To facilitate reading and writing, we can use data input and output buffers to make reading and writing happens quickly. Those data inputs can come from other banks, other places, and the output that goes out from the buffer will go to the memory bus and it will go to different locations. You can see this organization here is what we call is the 128 mega, which is organized as 16K in rows and 1K in columns, and you have 8 different banks. Each one of them will generate a single bit, totaling 8. If you multiply those 3 numbers, you will end up with the 128 megabyte. So from one cell, which is 1 bit, we organize them in rows and columns this way to generate 128 mega. And then we took this chip we repeat it 8 times for the front rank and 8 times in the back rank, and we end up with 2 gigabytes.